Professor Chen, can you share your screen and start?
Yeah, thank you. Thank you, Shaochen, for the nice introduction. Is this full screen or not yet?
Yeah, it's full screen.
Okay. Sounds good. Yeah, just a correction. I have not published like 1,000 paper yet. It's
100, sorry.
Yeah, 180 papers. So for 1,000, that's too much work to do. And on the other hand, I think in my own lab, we quite focus on quality rather than quantity. So yeah, so for today's talk, I will share my work in rapid 3D bioprinting engineered tissues with digital control of material properties. For disclosure, we founded Alago 3D company to commercialize the bioinks and bioprinters. And now this company is part of another public trade company called the Cell-Link or Bico Group. So for today's talk, I'll first give a brief introduction about the unmet needs in the society, specifically 3D human tissues. And then we'll talk about some of these biomaterials and printing technologies to process these materials. Then I will go to a specific topic about the 3D printing of functional nerve conduits from therapeutics perspective. Then I will move to bioprinting of functional tissue, mostly for disease modeling and drug discovery applications. And then I will summarize my talk. So our work has been motivated by two important societal needs. One is tissue repair regeneration. As you know, people are aging, live longer, and there are disease, and then often they're broken tissue, broken organs, and improve their quality. We need to learn how to repair them, how to regenerate some of these diseased tissues. From inner organ to outside, from top to bottom. The second important unmet need is drug discovery. It's also related to our healthcare, which means when a person is sick, you often need a medicine. And at this moment, it takes about 12 years and $2 billion to develop an FDA-approved drug. $2 billion. Okay, so it's a very long time. It goes from petri dish studies to preclinical studies. Then, if some of these compounds are still useful, they go to clinical trials. So the process is very long. The reason for this type of high cost, long time issue is that when you do this in a petri dish, usually it's a 2D human tissue model. They usually don't replicate well this 3D in vivo environment. So good data doesn't mean it will work. Second, when they go to animal model testing, so you probably know there's a species difference. Some of these drugs work very well for animal, but not necessarily for human. So I have an example. This drug is called fluoridin. It was developed to treat hepatitis B. The drug was tested very well in all these animal studies, mice, rats, dogs, and other primates. But when it went to human trials, out of 15 patients, 5 of them died, and 2 required liver transplantation. So that's a very sad story. They spent so much time, money on it, but eventually it failed at human testing. So is there any way that we can do this in a different fashion? That's really what we are trying to do, is to develop these 3D human tissue models to assist the process. So you can save the time. Let's say if I can save 6 years, then the drug can be done in 6 years instead of 12. Or if you can save the cost by, $1 billion, that's a lot of money, especially for these small companies or medium-sized companies. So that's how I designed my lab, to look at the way that how we can build these 3D human tissues. We focus on biomaterials because not every material works for biological cells. And then again, for these materials, we need new manufacturing technologies. Here we call bioprinting, to create these, to shape these materials into structure that we need. Okay, so we are talking about printing resolution, throughput, because resolution is important because we need to resolve cellular scale features. And throughput is also very important, time, because unlike traditional manufacturing, the piece can stay in the air or the dirty environment for a long time, but for bioprinting, you can't. These cells wouldn't survive for more than 2 hours outside the culture media. So these are the challenges. And then the last, we want to use the material technology to create these functional tissues for both in vivo and in vitro applications. When you go down to this direction, there are several important issues to look at. I'm more focused on engineering considerations in addition to biological concerns. So first is stiffness, because we care about material, right? So when you look at the different tissue types in the body, we have very soft tissue like fat, lymph node, brain, liver. We have medium-sized stiffness tissues like muscle, cartilage, and then on the top we have these bone and others, very stiff material. So we need an array of material that can meet different tissue types in terms of stiffness. Second is there are many dimensions of cell instructional materials, because the cell function is dictated by factors such as chemical composition in the environment, ligand density, network mechanics, cell shape that's imposed by the actual matrix, and the topology. At this moment, people have been successful in doing that in 2D for controlling all these individual components, but it has been quite challenging to solve these issues in a 3D fashion. Talking about 3D printing or bioprinting, Tony Atala's lab has a very nice review back in 2014. They talk about the inkjet printers that use inkjet nozzle to extrude those bioinks with or without cells, and then form this 3D structure drop by drop and layer by layer. Then there's another approach called micro extrusion printing. Basically, is a mechanical extruder to push these materials out line by line and then form 3D structures. So these are actually very straightforward mechanical system for printing. But as you may imagine that, if the material is very viscous, especially when the cell density is high, it's very hard to squeeze them out of these small nozzles, right? Particularly when we talk about cellular scale resolution. And then when you do drop by drop to form 3D structure, it often takes a long time. So we have been working on another types of printing called light-based printing. We start with laser processing. We call laser star lithography. Unfortunately, this name is really not layman. It's hard for people to remember. So later on the community called 3D printing. That's a much better name for this technology. So using light, you can cross-link these photosensitive monomers and form 3D structures. And if you use laser, you can do the scanning, dot by dot, then form 3D structures. And you can easily control the printing resolution, because that's something that we have been doing very well in semiconductor manufacturing, right? For making these electronics from micro all the way down to a couple nanometer now. So as an engineer, we always ask questions. Can we do better? In order to make a structure like this one, do we have to stack them dot by dot and then layer by layer? Is there any technology that can do this in a projection fashion? Then you can eliminate all these artificial interfaces that you impose in the structure, because these artificial interfaces, these interfaces are not per design, right? So from fabrication perspective, it's better to eliminate all these unnecessary artificial interfaces. So that's how we started with so-called projection printing based on digital micromirror devices. That you saw that in a projector, computer projector. So that was like 20 years ago. When I was an assistant professor, I didn't have a lot of time, a lot of money. So we bought like $400 BenQ projector, and remove some of these mechanical parts that block the access or make it harder for mounting. We use tapes, and here you can see this very old Dell monitor, very bulky. But it worked. This is a concept. We put together each components, lay them down on the table, and we made it work. Specifically for PowerPoint, we can run this slide by slide. And that's how we build this one layer at a time, and 3D, for 3D scaffolds. If you look carefully, you can see these lines between different layers. So that's really the nature of this traditional projection printing process. When you polymerize the first layer and move down the stage for the second layer to be built, you have to wait for the surface to be wetted. So that's how you create this kind of artificial interface between layers. But in the horizontal directions, you can manage this interfaces. So you can get smooth structures for that, and improve the speed of processing compared to the traditional extrusion-based process. And then it's just another idea, in terms of getting rid of these artificial interfaces. We took this idea called upside down. Right? When I teach graduate classes, we talk about these creative thinking methods. So one way is just putting things upside down. Well, if you do that, it's a very simple idea, but when you do this, it created a significant, very nice opportunity or totally different process. Here, the light comes from the bottom. When you cure the first layer, you can pull up, and then the second layer, third layer, fourth layer. So eventually, this fresh cured layer is always immersed in the ink, right? You don't need to wait until the surface is wet. It's already wet. So that allows you to do this so-called continuous printing. And benefit is speed. Of course, it's much faster. This can be done within a couple seconds to minutes. And I guess the most important benefit is the structure integrity, because now you don't see all these artificial interfaces in this 3D printed construct, right? And you can see here the surface is so smooth. You really don't see all these layers due to the manufacturing process. And it's so important for devices like in these tubes. This is most aortic models, and you don't want to have any of these defects that could leak the fluid, or if this is a medical implant, it may break down along the interfaces. So that's a really nice approach, just by redesign the machine using some simple creative idea methods like upside down in this case. So this really for making these single pieces. But when we talk to pharmaceutical people in terms of drug discovery needs, they always use well plates. They don't do this piece by piece manufacturing, and throughput is king to them. So we came back and figure out, hey, we can actually do the printing in a well plate if we redesign the system now by using an optical probe in this case, and this probe can be guided down to the bottom of the well plate. Then you can pull this probe or lower the stage in this case, and then you build these structures continuously in the well plate. So let me just show you the machine in action. You can see for each well, you can print within a couple of seconds, and then move on to the next well. And within each well, I can show you what exactly was being printed. In this case, is image-guided vascular network. This is for a mouse model. So you can see this is 11 seconds total, how fast it can go. And the resolutions, some of these small branches are on the order of 10 micron. So you can appreciate the speed and also the resolution. And this is the SEM image showing these details. So that's really nice for the pharmaceutical industry. People call this lightning fast 3D bioprinting. Just when fresh, you can get the stuff printed. So we started a company, and then the company were able to put all these different components in a box. So with the box, this machine can be sold, right? You cannot sell your technology by laying down pieces on the table. It need to be in a box. So this machine now is commercialized by CellLink and sold as Bionova X. They can print in all these different well types, 1 well, 6 wells, all the way up to 96 well plates. And a couple of micron resolution. You can do different cell types in the printing. You can also control the material property like stiffness for each print. Its speed is very fast, from second per well. And we also designed this with a mindset of environmental impact. So for biological processing, we often work in the biohood. So the machine needs to be small enough, compact enough to fit into the biohood to avoid contamination. And most important, I think the structure that's printed has very nice construct integrity without all these artificial interfaces I mentioned before. So if you have no experience in printing, I will just go through a little bit more details here. So within the bioink, you can, of course, you have this uncross-linked monomer. And you can, since it's in solution, you can add biological cells into it. And when we, culture these cells, often we need to have supporting materials. Sometimes, like these are biochemical factors and control release particles to help this tissue culture to grow. So now you mix them together, and they are uniform in terms of distribution. Then you shine light. Anywhere with light, you cross-link. Without light, they stay as a liquid. So that's how you generate a structure like this one. And then when you wash out this liquid, then you end up with a living construct. These cells are embedded in the gel. And then, then you can use this construct to do the post-printing process, to culture the cells, make into tissue and study them. Using gelatin methacrylate as an example, because that's a very good hydrogel biomaterials for tissue engineering. So you start with gelatin, you can massacrate it to have these extra arms. Then you can photopolymerize them under the light and the photoinitiator. Okay, so over the years we have developed a library of materials for bioprinting. That includes polyethylene glycol diacrylate. It's called PECDA. It's a non-toxic, non-immunogenic materials with tunable mechanical properties. And the gelatin massacrate, as I just mentioned, this material is biodegradable. It's also very important. It's cell adhesive, so they have all these natural cell motif on the construct for cell to attach. Then we have all this material called hyaluronic acid. It's also biodegradable, but we need to functionalize with cell adhesive protein like laminin to make it work. And if you want a little bit better mechanical strengths, alginate is another important useful polymer materials for tissue engineering. And then very often we could also decellularize these tissue organs and then use them as part of the scaffold material to facilitate cell growth in these tissue constructs. So, and you can control the material properties and material composition and the properties such as stiffness, right? So from biomaterial perspectives, if you go back to this original chart here, you could have different cell types, you could use different gels, and then you can add different nano or micro elements like nanoparticles or drug delivery particles in the systems. Then in terms of extracellular matrix stiffness, you can use different molecular weight gels. You can also control the gel percentage using the same gel but different percentage to get you different stiffness. And also related to printing is to really control the cross-linking density by varying the light intensity and the exposure time. And that's so easy to do with light-based processing, right? You can just adjust the intensity of the light and the exposure time of the system and get you good control, digital control of these material properties. So using JELMA again as an example, with a different percentage of JELMA, we can get different stiffness in terms of these scaffolds, okay? From 1 kilopascal all the way to say 15 or 20 kilopascal. And then also if you control the exposure time, then you can modulate this stiffness, from a couple of kilopascal to that. And that's really important for disease modeling because often, for using liver as an example, for healthy liver, the extracellular matrix stiffness around the 5 kilopascals. But if the liver is stiffered, then the material property is harder. It's on the order of 12 to 15 kilopascal, and this is called a cirrhosis liver. Okay, so using printing, you can easily control these stiffness to mimic the disease condition. Okay, so now let me guide you through some of these works that we have been doing in terms of therapeutics and drug discovery of tissue models. So in that, I'll first start with this printing nerve conduits. Okay, so people could have broken nerves anywhere from the facial to legs, and we have all these peripheral nerve supporting movement of the tissue, muscles. So if they're broken, we need to fix them. Traditionally, they cut off some other nerve from other parts of the body. Maybe not so important, but it's not spared, right? So it could be useful for repair. But then the issue is when you cut the nerve in other part of the body, then that part loses function. So it's not an ideal situation. So ideal situation, can we use engineering approach to repair this damaged tissue, specifically here nerve tissue? Okay, so we were using 3D printing. You can print all these conduits. We call conduits, just like a bridge for in a freeway to guide the traffic, right? So you could have these micro channels inside, or the conduit can be branched out like this branch out for fashion of these facial nerves. And then we can make a very large scale, this is centimeter scale conduits in fabricated by 3D printing. Okay. So we did an animal study. So this is the nerves in the left leg of a mouse. Shiny, both a bright field image and a CFP image. If this is broken, then we can put this conduits into the damaged site. And nice thing about 3D printing is you can measure the damaged gap, how long you need, and then you can print exactly the size you need, and snug this in using biological grooves, and then seal the wound. And after 11 weeks later, you can check how this nerve is being recovered. So you can see here those nerves grow nicely into these microchannels inside these conduits. Okay, we actually have also done this cross sections by take out this scaffold and check whether these nerves really grow into this different distance in the scaffold. So we look at different location of the scaffolds, 2 millimeter away from the starting point, 4 millimeter, 6 millimeter, and then end. You can see these nerves actually really grow into these microchannels and reach to the damaged ends or the distal ends. Okay, and we have animal testing for that. So this is the mouse with broken nerves on the left side of the leg, and it's not moving nicely. And with the help of these conduits, and this mouse actually got recovered after 8 weeks. So you can push the floor nicely, with function recovery. And so building on the success of this peripheral nerve studies, we move on to spinal cord, because this is more severe disease and there's no cure yet at this moment for repairing this damaged spinal cord. And this is more complex because for spinal cord you have, this is the image of the cross section of the spinal cord. You have gray metals, you have various neurons in different parts of this tissue. So we want to mimic that kind of structure through printing. Here we can print a same gray metal in the middle, we call butterfly H here, to enhance the overall structure integrity or property to hold off these structures. And then on the other side, other areas of the scaffolds, we print these linear channels. So and hope that we can put this scaffold into the damaged side to repair it. Again, nice thing about 3D printing is you can take digital images like a CT MRI scan in this case. This is the damaged spinal cord in a rat, and we can take this MRI data and replicate exactly the same copy of damaged site and put it back into the area for repair. So this is an overview of that. We can build larger structures per the needs of this specific injury. And then learning from another area is called stem cell therapy, is that people inject these stem cells into the damaged sites and try to repair these areas. So, but they struggle with cell death when they inject them, and the therapy is not being very successful. So we thought, since they don't have any control about these, where to put these cells, right? Once you inject them, they lose the control. Well, if we have a scaffolds, we can utilize these linear channels to locally control all these neural stem cells, okay? Instead of having them randomly aggregate. Here, we can organize them in this linear channel fashion, okay? And that's very important because now we can guide these axons into these individual channels to grow these nerves along the scaffolds. Okay, so this figure shows the neural stem cell field inside these channels, and these areas are the wall. If you think about these different channels, we put in the scaffolds, and this chart shows that the nerves really grow linearly inside this linear channel. Okay. And our data showed that this kind of combination is very important. We try a neural stem cell injection, okay? And the data in this specific case called a BBB score is to show how, some physiological appearance in terms of movement of the knees and toes. So for just injection of this neural stem cell alone, the score is very low, around 1. If you don't have neural stem cell, just empty scaffold, that works in the peripheral nerve case, but really didn't work for spinal cord, central nerve cells. And the data is even worse. But the combination of the neural scaffolds with the neural stem cell inside this linear channel gives much better outcomes. So that the BBB score is much higher, and if we can see some movement in the toe and the knees in the rat. So this work was actually reported by NIH director Brock when it was published back in 2019. So there's a hope that a spinal cord injury could be repaired in the future. So people are working on large animal models and even human trials using similar technology. Now let me move on to 3D printed functional tissues for disease modeling and drug discovery studies. So first, I would like to talk about liver tissue because talking about toxicity, every drug you take will end up in the liver, right? So if the drug causes the liver toxicity, then no matter this is an excellent cancer drug, it cannot be used. And you often heard that from your primary physician, whether the drug you take is causing liver damage or not. So we look at the liver. That's number one organ we want to look at. Then another important issue is there's a liver disease like liver cancer, like carcinoma, and that it's also a very devastating disease in our society. So can we actually build some sort of drug liver models for screening, for biological studies and disease modeling? So to do that, we look at some physiological conditions, so look at the architecture of the liver. That's actually very complex, right? You can see the liver has multiple flows, the portal vein, artery branch, central veins, and multiple cell types in the system, hepatic cells, endothelial cells, and many other supporting cells. So we need to look at these, microarchitecture. We need to think about different cell types to build a biomimetic tissue. And then importantly, also from engineering perspective, what material to facilitate these type of tissue, okay? So we start with just printing how we can control the patterns. right? So first we can design a pattern here with for the hepatic site. It means, in these white areas inside the hexagon, we'll print these hepatic cells. And then the dark areas will be filled by these endothelial cells and other supporting cells. So we were able to replicate that kind of design, and with the resolution we need. So these are about 20 microns in size of these, hexagon lines. And then we move on to the live cell printing for the hepatic part. We use human-induced peripheral stem cell with a goal of building human-like liver tissue. So these are hepatic progenitor cells. And we managed to use gelatin as a material because the stiffness of gelatin matched very nicely with healthy liver tissue. Okay, and then mix these cells and gel together, shine the light, and you create this hepatic part in green, just within a couple of seconds in terms of printing. Okay, this is about 3 millimeter by 3 millimeter size that we printed within a couple of seconds. Then you wash out the leftover, and so now you have these lines, hexagon lines, and some other lines that was empty before. You can put another group of cells, in this case HUVEC cells and adipose-derived stem cells, along with the gelatin with some content of hyaluronic acid, because HA will support well these HUVEC cells. So another exposure, you will print these cells inside these empty areas after first print. So by 2 steps of printing, we can create this very biomimetic liver construct based on these iPS-derived cells. And this is a 3D reconstruction. And we want to make sure now, these are liver tissue. So, right, we measure the key genes, liver-specific genes. And in doing so, we want to compare our model with multiple cell types. Here we call triculture models, with traditional 2D monoliths, just hepatic cells in a 2D, in a petri dish. And also the simple model without supporting cell, we call 3D hepatic cell only model. And you can see these 3 major genes, albumin, HN4 alpha, and TTR, have much higher expression levels in our 3D triculture model in comparison to 2D and hepatic only, 3D hepatic only models. Okay, and for fetal hepatic marker alpha fetal protein AFP, we don't see significant difference, but we see a gradual reduction from the 2D model to our 3D triculture model. So this is nice. We have printed a liver-like structure, okay? And then we want to measure the function, whether this liver can do something, right? So specifically, we look at albumin secretion levels and the urine production. Okay, again, we compare our triculture model with 2D and the 3D simple models, and we culture them for about 40 days. And these are the data showing the results in comparing to the 2D and 3D simple models. Our triculture models show much high level of albumin secretion level. Same thing for the urine production. Okay, over the time you do see some decline from day 5 to day 20. I think that's because we use these iPS cells and they are mature enough. But hopefully, in the future, we can improve that. Okay, and then we went on to just to a pilot study for drug testing. Specifically, we look at this antibiotics called rifampicin. Okay, And we dose this rifampicin into these tissue cultures and compare our results with those situations that has no drug dose. Okay, as you can see, for these three major CRPs enzymes in the liver, CYP3A4, 2C9, and 2C19, our triculture model has much higher level of expression for these major threes. And in contrast, the other two, the 2D model and the 3D simple model, really do not show significant difference between the control and the tissue. So this is some sort of a good indication that using 3D bioprinting, you could create these human-like tissue for drug testing. For rifampicin, we know, but for pharmaceutical company, when they develop these new compounds, and now you can quickly test them out, whether they are toxic, whether they are useful for treating diseases. Okay. And our next model, if I don't tell, you can imagine that's heart, because heart is such an important organ in our body, and heart disease is also very devastating for many people in the U.S., also in the globe. So we will look at building a heart tissue that could be used for drug testing, for instance, like I just discussed, and maybe also for disease modeling. Okay, in parallel to assist the traditional route using 2D culture and the animal models. Okay, so we start with just mixing the cardiomyocytes with the gel and print them. If you culture them for a couple of days, they start to beat. Okay, but if you do a little bit engineering by pattern these tissue construct into lines, it means these cells are communicating better in this line fashion, then you can see the beating is quite different. Okay, quite different. So using some engineering approaches, you can actually change the nature of this tissue construct. Okay, so the question is, how do I can see the frequency of beating, but what's the force outcome of this cardiac tissue? And that's also often very important to evaluate this cardiac tissue. So we developed this so-called instrument heart tissue, or heart on a cantilever. So we can actually 3D print these cantilevers in the plate, and then print this cardiac tissue around these two cantilevers. Particularly, we designed this cantilever system with one very thick and sturdy, so it's stable. The other one is very thin, so when the cardiac tissue contract, when it beat, they will tend to deform this smaller cantilever, and that deformation tells us the force generation by this cardiac tissue. So we actually have a very nice equation to describe this displacement and the force, right? So that's the beauty of engineering. We have these equations. Okay. So here you can see this cardiac tissue that's beating. When they beat, they pull this thinner cantilevers. If you look this in larger view, you can see that. So from that, we can measure the displacement. And from the displacement measurement, we can calculate the force generated by this cardiac tissue. And also, as I mentioned, that with this kind of in vitro tissue model, we could test out some drugs. Okay, so we test out 3 drugs. This is isoproterenol that has been FDA approved to treat bradycardia. It's basically slow heart rate. And another 2, vivo and omecamtiv, both are not being approved by FDA yet in the United States. And we want to see how they are doing in terms of enhancing the beating force or not, right? Or beating frequency. So we compare our drug treated model with control. It means there's no drug in dosing. So all 3 actually increase the displacement or essentially the force of this cardiac tissue. So in the future, people can use this model to test out other new compounds they are developing, okay? And as using 3D printing, we can create a library of different types of organization of this cardiac tissue. In this case, a slab means just no pattern, just a slab. You can see the beating is very random and not organized. Lines, like you see here, is much stronger. We can also print the grid. So we have all these cross in the system. And then you can see also the beating is reduced. And then dispersion case, with this kind of shrinking. And you can, you don't see really the significant force generated by this. And the last one is just a random organization of these lines. And you can see also the difference between this and others. So with 3D printing, you can easily create all these library of different patterns of the cardiac tissue. And if you look at these cells, cardiac cells in the construct, you can see quite difference in terms of how they interact with each other. This is much aligned in this line case. And for grid, for slab, for dispersion, and a random case, this alignment degree is much worse. Okay, much worse. So far, we talk about liver and the heart. The field is moving towards the future in terms of organ printing, and we have to realize that in our organ, the cell density is much higher than what we can handle. So typically in the current tissues that we build for the liver and heart, the cell density is about a couple of million cells per mil. And in reality, in solid organs, the cell density is on the order of a couple of billion cells per mil, okay, or per volume for that specific volume. So there's a huge gap between that. And the reason for that is for traditional extrusion printing, you really cannot put too much cells in that because you're going to damage cell membrane, and it's so viscous to push through. And for light-based printing, we also have this issue, but it's related to light scattering, because the refraction index of the cytoplasm is quite different from the bio ink we often use. So when you shine light into a media with all these isolated cells with different refraction index, you can imagine you have lots of scattering. If you have a scattering of the light, then you really don't have control of this light-based printing because the light are scattered. You don't form the pattern you need. So we tested out in this case just by choosing the specific pattern we want to demo. Without cells, of course, you can print nicely, right? Because we could have a couple of micron printing resolution. And then we can resolve all these details per the design. Now, if you add cells, okay, add cells to just 100 million cells per mil, you can see the scattering causing problems. Here, you really don't see this, end point of these flowers and snowflakes. So it has been challenging for the field to print high cell density towards organ manufacturing in the future. And typically, as I mentioned that, so far we work with a couple of million cells per mil. So how do we do that? How do we print high cell density for future organ manufacturing? Well, we can learn stuff from other fields. So that's another creative thinking method, learning from other fields, in addition to upside down design, right? So we look at this material called iDixonal, and this is a FDA-approved material for contrast enhancement in CT scan and X-rays. Okay, when you add this iDixonal into the tissue, then you can have better image. Okay, so we look at that. This iDixonal has actually a higher refractive index, okay, about 1.4 something. So we mix this iDixonal with our bioinks by certain percentage. We try, 20%, 30%, and you can see the refractive index is quite different. You can actually tune the refractive index of the system to optimize the light penetration. So we also did simulation that with 0% of the iDixonal, if you shoot a light into the bioink, you can see all these blurred images. And that's an issue for printing, because if image is blurred, you cannot create this structure. Well, if you add iDixonal in the solution, in this case by 30%, then you can see these patterns preserve its shapes over a distance about 400 microns. So that's really nice. And then we test out. In this case, you can remember all these old cases you couldn't resolve when you add 100 million cells per mil. Now, if we add iDixonal into it with 100 million cells per mil, you can still get clear patterns, in the print. So that was really interesting advancement for the field. But of course, when you add stuff in the ink, you always need to make sure that this addition will not cause viability problems. So we check, whether they're toxic or not, right? Even though this is FDA approved, we also want to check whether it will work for our inks. So we put the HUVAC cells in the JELMA and mix it with the iDixonal and check out the cell viability. It doesn't change. Same thing for this other cell types, C2, C12, HCs in different bioinks. This is hyaluronic acid, this is alginate. So with these studies, we are confident that this strategy will work. And then we went on to build this vascularized thick tissue. This is about 3.6 millimeter thick. It's to tissue engineering, this is very thick. Usually when we talk about building tissues, we worry about diffusion limit. That's about 250 microns. So we build a very thin tissue. Here, if you build 3.6 millimeter thick tissue, you definitely have to have vasculature support in the system. But if the cell density is high, then you couldn't print this structure inside, right? So with the help of iDixonal, we made this very thick tissue, and we vascularized this construct. You can see that the lumen formation within this vasculature network. Okay, so that was very useful for future manufacturing of thick tissue supported by vasculature network. So to summarize my talk, I hope I show you that this DOP-based printing is very useful for 3D tissue manufacturing with digital control of material properties in terms of resolution and speed, shape, porosities, stiffness, multi-cell architectures. And then we talk about direct in-well printing. You can build these structures inside the tissue without transferring from your glass slide to the well plates. And we showcase the liver tissue and the cardiac tissue models for high throughput drug testing in the future. And adding iDixonal to the bioink will allow us to do high cell density printing towards future organ manufacturing. So, and definitely, I talk about many years of work. So we have a generation of students working on the projects. Now they are part of this community, either in university settings or these biotech or other high-tech companies. In a lab, we often maintain 10 to 15 people, plus many undergrads. They just love to work on 3D bioprinting because when they see the beating heart in their well plates, they're just excited. And at the UCD, we were lucky enough to have a medical school on campus. I collaborate with people in cardiology, cancer centers, pathology, and many other departments. And the work group has been funded by different funding agencies, NSF, NIH, and particularly I'm very proud to say that many NIH institutes are interested in building different disease models for liver, heart, nerves, cancer, and children disease. And then I'm in terms of location, I noticed that we share the same time Zoom. I thought you guys are mountain time and luckily I checked the time for the presentation. So thank you. I made my presentation on time. And I noticed that we are very close to each other. I think in terms of driving, we could get to your place faster than going to Los Angeles. Sometimes the traffic in Los Angeles is just terrible. So if you have time, please come to visit us. We are here right on the Pacific Ocean beach. We have a La Jolla shore. Here is a medical school and engineering school. So with that, I would like to conclude my presentation. I will be happy to answer a couple of short questions. Thank you so much.
Thank you very much. Very impressive talk and impressive work. All right, so any question from the audience? I have collected 3 questions from audience. So I think the first question is from Sahid. Sahid is interesting, like how did you control the printing resolution?
Printing resolution, yeah, okay.
Yeah.
That very good question. So I think that's very much on the optics side, right? So you can design this system, light optics, projection optics, to get down to a couple of microns. But also I think the resolution depends on the chemistry, right? Because it relies on the photopolymerization. You have free radical generation and diffusion, and so you need to optimize the exposure time, diffusion time, so to get you the best resolution you can. So it's a system engineering.
And I think your talk, your slide has already answered the second question. So there's another question is, so in your printing, how did you guarantee and keep the cells alive during the printing, especially when you are using the UV light to photopolymerize the monomer?
Yeah, we actually we start with the UV, so people always have this concern, but later on we move to 4 or 5 nanometer light. So it's outside UV, it's a blue. So that really remove their concern. But I think more importantly is how you handle these cells. So especially for stem cells, if you don't handle them well, you can add stress, you can induce contamination, then that's an issue. Printing itself, I think, is pretty straightforward.
Got it. Any other questions from audience? All right. So if no more questions, let's thank the speaker. And I know Professor Chen has another appointment at 12 p.m. So let's thank the speaker.
Thank you, guys.
Okay. And okay, thank you, Professor Chen. Looking forward to see you in person next time.
Sure, yeah.
Yeah. Okay. Bye-bye, everyone.
Bye.